You've heard this before. The star you're looking at right now might already be dead. Its light traveled for years, sometimes thousands of years, to reach your eyes. And what you're seeing is a recording, a delayed signal from something that may not exist anymore. That's a small delay. There's an object in our universe where this delay isn't measured in years. It's measured in billions of years. And not just any object. The largest known consumer of matter we've ever found. Its name is Phoenix A, and while you watch this video, we are looking at a version of it that hasn't existed for almost 6 billion years. The version that exists right now, at this exact moment, we will never see. Not us, not our children, not anyone who will ever live on Earth. In the next 14 minutes, we'll explain what Phoenix A actually is, why nothing about it adds up, and what it could have become in the time we've been blind to it. In 2012, a telescope buried in the ice of the South Pole began picking up something strange. The South Pole telescope wasn't looking through the universe in visible light. It was looking at distortions in the cosmic microwave background, the faint glow left over from the Big Bang, searching for places where that glow had been bent by something massive sitting in the way. It found a lot of things, but one of them stood out. A galaxy cluster, hidden almost 6 billion light-years away in the constellation Phoenix. Astronomers cataloged it as SPT-CLJ2344-4243, but nobody calls it that. They call it the Phoenix cluster, and once they pointed the right instruments at it, they realized they had discovered something that shouldn't be possible. The Phoenix cluster weighs roughly 2 million billion times the mass of our Sun. That's 2,000 Milky Ways fused into a single gravitational structure. It is one of the heaviest things in the observable universe. It also emits more X-rays than any galaxy cluster ever measured, over 8 × 10 to the 45th ergs every second. To put that in human terms, every second, the Phoenix cluster releases more energy in X-rays alone than 2 trillion suns produce in the same second across all wavelengths combined. At the very center of that cluster sits a single galaxy. Astronomers call it Phoenix A. It's one of the largest galaxies ever observed. Its visible disk stretches over 360,000 light-years across, more than 3 times the diameter of the Milky Way. And in the center of that galaxy, anchoring everything, is a black hole. This is where the story stops being a description and starts being a problem. Because the more we measured this black hole, the less it behaved like a black hole should. Here's what's supposed to happen at the center of a massive galaxy cluster. Hot gas, millions of degrees, spread across millions of light-years, sits in a delicate balance. Gravity pulls it inward, trying to make it collapse and form new stars. But the supermassive black hole in the center fights back. It feeds on a small fraction of that infalling gas, and the energy released by that feeding launches enormous jets of high-speed particles. Those jets carve cavities through the cluster. They send shock waves outward. They heat the gas back up faster than gravity can cool it. Astronomers call this AGN feedback, active galactic nuclei feedback. It's the reason most galaxy clusters look quiet. The central black hole acts like a thermostat. Gas tries to cool. The black hole heats it. Equilibrium holds. The Phoenix cluster broke that thermostat. In Phoenix, the gas isn't being held back. It's pouring inward. Astronomers measure something called a cooling flow, the rate at which hot gas condenses and falls toward the center. In normal clusters, this rate is small or close to 0 because the feedback mechanism is doing its job. In Phoenix, the cooling flow is roughly 3,800 solar masses every single year. It is the highest cooling rate ever recorded in any galaxy cluster anywhere. And the consequence of that runaway cooling is even more extreme. In a typical galaxy, new stars form at a rate of about 1 solar mass per year. Our Milky Way is a quiet, well-regulated factory. Inside Phoenix A, new stars are being born at a rate of 740 solar masses per year. 740 times the production of the Milky Way, all concentrated in a region just 20,000 light-years across. This is something no model predicted. The black hole at the center of Phoenix A is supposed to prevent this. It's supposed to be doing the same job that every other supermassive black hole in every other massive cluster is doing. It isn't. Either that black hole is too small to control its cluster, or there's something fundamental about how supermassive black holes work that we have wrong. And here's where the second mystery begins. Because when we actually try to measure how big this black hole is, we get two completely different answers. Measuring the mass of a black hole almost 6 billion light-years away is not a direct process. You can't put it on a scale. You can't even resolve its event horizon. The disk that the Event Horizon Telescope captured for the galaxy M87 was 1,000,000 times closer than Phoenix A. For Phoenix, you have to infer the mass from indirect signals, and there are two main ways to do it. The first method uses X-ray data from NASA's Chandra Observatory. By measuring how the hot gas behaves near the cluster center, astronomers can estimate the gravitational pull of whatever is anchoring it. That calculation gives a black hole mass of about 5.8 billion times the mass of our Sun. Already enormous, comparable to some of the largest known supermassive black holes. The second method, developed by Brockamp and colleagues, uses a different approach. It looks at the density of stars in the innermost region of Phoenix A and models how the black hole would have grown over cosmic time, fed by stars and gas falling into it. That calculation gives a very different answer. 100 billion solar masses. Not 5.8, 100. Roughly 17 times more massive than the X-ray estimate. If the higher number is correct, Phoenix A is the most massive black hole ever discovered, larger than the famous TON 618, which weighs in at 66 billion suns. But the higher number isn't just record-breaking. It sits exactly at the theoretical ceiling. A 2024 study by Priyamvada Natarajan at Yale and her colleagues calculated the maximum mass any black hole in our universe can plausibly reach. The answer they arrived at was around 100 billion solar masses. Beyond that point, the natural feedback mechanisms that supply matter to a growing black hole begin to shut themselves off. The black hole runs out of food. If Phoenix A really weighs 100 billion suns, it isn't just exceptional. It is at the edge of what physics allows. And if its event horizon scales accordingly, it would stretch almost 600 billion kilometers across, 100 times the distance from the Sun to Pluto. The entire solar system, every planet, every comet, the Kuiper Belt, would disappear inside that event horizon without disturbing the surface. Both estimates can't be right, and nobody, today, knows which one is. But here's the thing, and this is where the real story begins. Both of those estimates describe a state of Phoenix A that ended a long time ago. Light moves fast. From Earth to the Moon, just over a second. From the Sun to the Earth, 8 minutes. To the nearest star, 4 years. To the center of our own galaxy, 26,000 years. To the Andromeda Galaxy, 2.5 million years. To Phoenix A, 5.7 billion years. That number doesn't compress easily. 5.7 billion years ago, the Sun did not exist. The Earth did not exist. The atoms that would eventually become you were scattered through interstellar gas clouds that hadn't yet collapsed into our solar system. What we see when we look at Phoenix A today is light that left it before our planet was a planet. Whatever was happening at Phoenix A in that ancient moment, we are watching it now. The runaway cooling flow. The 740 suns per year being born. The black hole growing, or stalling, or merging with something else. We don't know which because the recording stops there. The light didn't. For 5.7 billion years, Phoenix A kept existing. It kept doing things. It kept eating or starving or colliding with neighbors. Galaxy clusters of that size are still actively merging today. The Phoenix cluster itself shows signs of a recent merger that may have disrupted its central black hole's ability to control the gas. If that merger pattern continued, other massive galaxies could have fallen into the central region. Their supermassive black holes could have spiraled inward, lost orbital energy to gravitational waves, and finally collided with Phoenix A itself. If even one such merger happened, the black hole we see today no longer exists in that form. It has been replaced by something larger. If multiple mergers happened, and over 5.7 billion years, multiple mergers are likely, the modern Phoenix A could be something for which we don't have data, don't have models, and don't have a name. Or the opposite could be true. Maybe Phoenix A hit the theoretical ceiling that Natarajan's team calculated. Maybe the feedback finally caught up. Maybe the runaway cooling stopped. The starburst extinguished itself, and what was once the most violent center of any known galaxy cluster became quiet, a sleeping giant in a graveyard of burnt-out stars. We genuinely don't know which version is real. And here is the part of the story that's hardest to sit with. Suppose we wanted to find out. Suppose we built a probe, a perfect probe, capable of any speed below the speed of light, and aimed it at Phoenix A today. It would take more than 5.7 billion years to arrive. By the time it got there, our sun would no longer be the sun. It would have left the main sequence, swelled into a red giant, swallowed Mercury, swallowed Venus, almost certainly destroyed the Earth. The oceans would be gone, the continents melted. There would be no humans left to receive a signal from that probe. No descendants of humans, no archaeological trace of our species. Anything we sent to investigate Phoenix A would arrive in a universe where Earth had stopped being a place where life could exist. Even a one-way signal, a radio transmission at the speed of light, wouldn't fare better. It would arrive in the same future where nobody on this planet remains to follow up. Nobody alive today, and nobody who will ever live on Earth will know what Phoenix A actually is right now. The information exists somewhere in the universe. It is simply, structurally, permanently unreachable from where we stand. The window we have into Phoenix A is one-directional. We can look, we cannot ask. And here is the thing that quietly extends the entire problem. Phoenix A is not unique in this way. It's just one of the most extreme examples. Every distant object we observe is, by definition, a recording. The Andromeda Galaxy, 2.5 million years old when its light reaches us. The faintest galaxies JWST has been observing, nearly 13 billion years old by the time their photons hit the telescope's mirror. Even in 2025, when astronomers used JWST to map the cooling flow inside Phoenix for the first time in mid-infrared light, what they were really mapping was the same 5.7 billion-year-old snapshot, just in slightly more detail. The map of the universe we hang on our walls, beautiful, scientifically accurate, color-coded by redshift, is a composite of moments that never existed simultaneously. It is a collage. Andromeda's contribution comes from when the first hominids were standing upright on the African savanna. Phoenix A's contribution comes from before the Earth condensed out of dust. JWST's deepest fields contribute light from when the universe itself was a different kind of place. There is no single instant in which all of those scenes are happening together. We have stitched them into one image because that is the only kind of image we are capable of seeing. There is no view of the universe in the present tense. If you've made it this far, you're someone who actually wants to sit with that idea instead of brushing it off. The algorithm pushes videos like this only when people stay through them. So if the question of what's actually out there, what's still out there, right now, while we look at the ghost of it, is the kind of thing that doesn't let you sleep, subscribing helps more of this reach you. And if you want to say which deep space object disturbs you most when you think about it this way, leave it in the comments. There's a good chance the next ghost we examine comes from that list. The star outside your window might already be dead. That's a local delay. Phoenix A is a cosmic one. We are looking at the brightest, most violent, most matter-hungry object we've ever cataloged. And we are looking at a version of it that almost certainly no longer exists. Somewhere in our actual present, in the present tense of the universe, there is a real Phoenix A. Maybe it has grown into something physics doesn't allow. Maybe it has gone quiet and become a tomb. Maybe it has merged with a sibling, and there is no longer a single object at all, but a binary that will eventually become something neither of them used to be. We will never know which. We are watching a ghost, and in the meantime, the thing the ghost used to be is doing whatever it is doing, alone, 6 billion light-years from anyone who could ever care.